Okay, so it is exactly 6 p.m. Belgrade time and 9 a.m. Vancouver time. Let us start this lecture. Good evening, everyone in Europe. It is my great pleasure to have opportunity to invite Professor Tony Young. I'll say a few words. By the way, my name is Svetlana Berzev. I'm president of Serbian Association of Earthquake Engineering. And this is our first talk, first seminar for this year. Professor Tony Young is a very dear colleague of mine. I'm also affiliated with the University of British Columbia, where he, in Vancouver, Canada, where he is a full-time professor. I've been impressed by his energy and breadth of interest and support for graduate students. He is at the University of British Columbia. Professor Young is a renowned expert in the field of earthquake engineering in Canada. He's a member of the Code Committee for the National Building Code of Canada, which develops provisions for seismic design provisions and also for steel design code as well in Canada. And he teaches a number of very interesting subjects, including advanced design of steel structures. I had the opportunity to attend a couple of his lectures, and then innovative technology, then earthquake engineering, earthquake resistant design, or something like that. Not sure what is the title of the course. He has been involved in design of tall buildings or in the Tall Buildings Council. He has been, I believe, executive director at the same time while being a professor at UBC, a director of the Earthquake Center at Tongji University in China, one of the most important in Shanghai, one of the most important centers of that type in, I would say, in Asia and in the world. He's very active in the development of innovative technologies that he is going to share with us tonight with his students. And I have an opportunity to work with him on masonry projects and support the students who are working at University of British Columbia. There is a group, and I sent a link to the site, which he is leading with more than 40 students and associates. So without further ado, I would like to introduce Professor Young and invite him to start with the lecture. The lecture, I would like to say, you'll be all muted during the presentation. And then after, which probably around 1 hour or maybe slightly less, you'll have opportunity to ask questions. I'm going to moderate the discussion. Tony, please go ahead. Thank you.
Thank you so much, Professor Brazat, and thank you so much for inviting me here to these important meetings. Svetlana has mentioned so many great things about Belgrade and had invited me to visit it, and I look forward to have the opportunity to visit Belgrade in person very soon. Professor Brazat is a longtime colleague of mine, and I'm very fortunate and very lucky to have the opportunity working with her. And also Professor Stojadinovic, my mentor, my advisors in my PhD programs here as well. So I'm very grateful for both of you to attending this lecture. My name is Tony Young. I'm one of the professors in the Department of Civil Engineering at the University of British Columbia, Vancouver. So today, Professor Brazet asked me to give some presentation related to the high performance system that we have developed here in North America. So I prepared my slide and we all heard about that, and I was chatting with Professor Brazet as well. Recently, there's a big earthquake in Turkey and we all heard about it, and it's felt worldwide. So I dedicated my first slide to the lives lost at this significant earthquake. Hopefully us can do better in the future to make sure the casualty rate are lower worldwide. So my first slide here for the presentation is, why do we care about earthquake? Well, we felt about it, and clearly Serbians are creating an association for earthquake engineering, means that you care a lot about earthquake as well. But in many parts of the world, people say earthquake are not my problem. It's from somewhere, maybe in Japan, maybe in New Zealand, maybe in the United States, they have the earthquake problem, not us, okay? So as I started looking and learning earthquake, earthquake is important to everyone live on planet Earth. Why do we have earthquake? Well, the Earth was formed about 4.5 billion years ago. The star, can you hear me well? No problem. Yeah. So when the stars are colliding in the space, and there's a lot of heat trapped in the middle of the Earth, and space is very cold. So suddenly the Earth covered, the center of Earth are very, very hot, and space are very, very cold. So suddenly the heat are trapped inside the center of the Earth. If today we have the technology to cut the Earth open, you will see this energy in the center of Earth is constantly radiated out to the space, because physics telling us heat is traveling from hot temperature to cold temperature, so that heat is released all the time. So today we don't have the technology to really cut through the Earth, understand every layer of Earth underneath us. So it's very difficult for us to really model the entire Earth. But over time, we see in some pocket of the Earth, the heat get released over to the space, and then that's where we have earthquake faults. Sometimes they are beneath the ocean, sometimes just right underneath our building. So if you say, I live in the places where I have no earthquake, it's not true. It's just that we haven't had the technology to detect it. In fact, some of our colleagues from Japan are predicting the entire Japan, the whole country, could split into half, east and west direction. So, it could be north and south direction, split into two parts for the entire Japan. So prediction models are there. Now we take a look of a picture. This is 1906 San Francisco earthquake. This is a real photo taken after earthquake. It shows us how significant the natural hazard is. This earthquake completely destroyed the Golden City of the United States. 80% of the entire San Francisco was suddenly destroyed. And at that time, over 3,000 people were reported death. And more importantly, half of the population have nowhere else to go home. So when people have nowhere else to go home, instead of immigrate to a city, they emigrate out of the city. It takes longer time, more resource for the city to rebuild. You may say, Professor Yang, this is 1906, more than 100 years ago. These 100 years, we have done a lot of good work in earthquake engineering. Yes, we do. We have done a lot of good work, but we have not fully solving the problem for earthquake. In 2011, the Christchurch earthquake completely destroyed the second biggest cities in New Zealand. And to a small population country like New Zealand, the entire second city was completely wiped out. It caused a direct financial loss of 35 billion US dollars, direct losses. So these are the money we pay to replace the property loss, the buildings, the infrastructures. But the indirect loss, including loss of business and the money we pay for human life, which we don't know how to evaluate that, and the loss of business are way beyond these direct financial losses. $35 billion sets back the GDP for New Zealand for over 10 years. Well, you say New Zealand is a small country. Let's take a look at the 2011 Tohoku earthquake. The countries which is most prepared for earthquake and are dealing with it all the time, this Tohoku earthquake are seeing a direct financial loss of 235 billion US dollars direct financial losses. A whole sector of Japan was completely wiped out through this major disaster. No country in this planet, not the United States, not Japan, not China, not Canada, or European add up together can withstand the big financial losses like this. So let's take a look at how we deal with earthquake engineering design in today's state. So in today's state, we look at performance-based design. We understand there are frequent earthquakes and there are very rare earthquakes. And the idea behind it is that when you have a small earthquake, we want the building to actually have some damage and some cracks here and there, but we want to make sure the light still go on, the water still running, we can go back and immediately use it. On the rare earthquake comes every 2,000 years, maybe like the one we see in Turkey. We will expect the building to be badly damaged and dissipate the earthquake energy, and hopefully it do not collapse. This is the design philosophy. We have been using it in North America and probably adopted from around the world. We want the building to be badly damaged. With the idea that earthquake may or may not happen during the design life of the building. But unfortunately, earthquake is going to happen. It's not if, it's when. How good would that design be if an earthquake will happen to your city? In 2011, our colleague in New Zealand suffered major damage. So this is Christchurch, New Zealand. The casualty rate are low, but the entire downtown central business district are completely destroyed. How good will a design be? How good will the government policy be if 70% of downtown will be demolished? And yet, many more of them are severely damaged and need to be either significantly repaired or need to be torn down. Well, there are high-performance systems which have already been developed, and it's not a sci-fi movie. The Japanese has already developing these high-performance systems. And this is a building right in downtown Sendai through the 2011 Tohoku earthquake. The building moved 23 centimeters during the earthquake. The building, every glass is fine, the electricity and the water is running. Buildings experienced this major earthquake and no damage happened to the building. So it's not something that we cannot design for, and it can already, the technology is already there. This is another example in Taiwan, Taipei. People are selling this kind of apartment, showing this luxury content with the spa, with the interior finishes. But what I'm very impressed about what the Taiwanese and the Japanese are doing, they consider comfort and safety equally. So they will pay expensive content they have over here, but they also pay a lot of attention to the earthquake hazard. So in this building, they utilize the viscous wall damper developed by Japan. So in the event of earthquake, the building actually can sustain a lot of shaking without damage. So at UBC and in many parts of the North American universities, we're developing high performance systems. So I'm going to show you a few high performance systems in today's lecture. One of them is what we call the steel link column frame. Maybe some of you have heard about this kind of system. Maybe some of you have not heard about it. Well, steel link column frame is very similar to what we see as a conventional steel moment resisting frame. Architects like this kind of structure. They have big window, very easy layout. So you can do a lot of planning inside the building. So no bracing to block it. But because the design of the moment resist frame are designed to bending the beam and columns, so moment resisting frame by nature are very flexible. So during the earthquake, the flexibility is going to cause a lot of damage to structural and non-structural components. So engineers in North America were saying that, well, the architect liked the big opening and we have to increase the stiffness to reduce the drift. So the thing they do, they started making the beam and column very beefy so they can increase the stiffness and still keeping the big opening. Unfortunately, this is chasing our tails where you're having a bigger column, a bigger beam, then the bigger column, and become very uneconomical. So at that time, we were working with the Canadian Institute of Steel Construction. We say, how about we don't put the money where the beam and column are? We'll use just the conventional beam and column. But we know we want to keep the big opening, but we want to increase stiffness. One way of doing it is putting braces, but architects don't like it. So what we end up doing, we places a very closely spaced column and with many steel link beams in between. The steel link beam provided two advantages. One, it provides additional stiffness to the structure. Two, it provides the energy dissipation needed so that in the event of earthquake, those link beams will dissipate energy to shield yielding of the links. And we can add as many links as we want to actually dissipate additional energy in protecting the structural system. If you take a look of the force and deformation relationship of a steel link column frame system, at the beginning, you have the moment resisting frame, which will initially behave elastically and eventually up to a certain deformation, any structure will yield. Okay. And in this situation, we added the steel link columns, steel link beams, where the link beams will provide additional stiffness to the structure and it will yield it earlier than the moment resisting frame. The combination of the moment resisting frame plus the link beam will create a new trilinear force deformation system, which is the link column frame system. So in this situation, if the earthquake is actually small, so between 0 to Fy, so in this situation, our structure will remain in this region, where both my moment resisting frame, the primary system, and the structure fields will remain elastic. We will call this kind of performance immediately occupancy. If the earthquake goes beyond the Fy value, and it goes beyond, but it's less than Fp value, so the earthquake is within this region, then the moment resisting frame still remains elastic, but our link beams started yielding, so it dissipates energy. So after the earthquake, we can go back to the building, take out both the link beam and put the new link beams in, and the building can quickly recover to damage-free. So we call that rapid return of performance. Of course, we still want to make sure what happens if the earthquake goes beyond what you designed it for, and it's very likely because the earthquake hazard is just a prediction. If it goes beyond where we're going for, we want to make sure even the primary system has some energy dissipation so it can yield it as well to provide the collapse prevention performance. So that's the trilinear force deformation performance system that we started developing almost all kind of the high performance system we're developing now. Let's take one step back and take a look how we do the traditional design for conventional seismic force resistant system. If I'm a building owner, I have to build a 4-story apartment, for example. I will hire an architect, says I would like to have X number of rooms and needed to have a window. And what the structure engineer will do, the architect will hire a structure engineer and say, please design a structure system to work for me. Structure engineer will look at the structure and pick a structure system to work. So in this situation, because there's an opening, probably moment resisting frame will work well. It can hide around the window. So the structure engineer can pick the structure system to fit the architecture need. And with the structure system it has, and the structure engineer will have some feeling about what kind of structure period it has, what kind of ductility, and what kind of overstrength the structure has. Next thing, the structure engineer will say, okay, I'm going to design a moment resisting frame building, let's say in Vancouver, British Columbia, Canada. Then I know the seismic hazard at that site, so I know what kind of shaking the building has. Okay? Afterwards, the structure engineer will calculate by the building code what kind of earthquake forces we should be designing for. So a lot of the time, it will be proportional to the shaking, the mass, and almost inversely divided by the ductility and overstrength factor. In the North America, in United States, we have a simple R factor. In Canada, we have a ductility overstrength factor, but they behave the same. Later on, the building code will teach you how to go from the design forces you have as a base shear to distribute it over the height of the building. With that, structure engineers started calculating how much axial shear and moment capacity in each of the beam and columns.
Then they will size the beam and column accordingly, and they check whether the drift is sufficient. The structure has enough drift, stiffness or not to limit the drift of the structure. If the stiffness is sufficient, then we will move on to the design. If the stiffness is not enough, the engineers will go back and resize the member and until you have enough stiffness in the system and enough strength. Finally, once you have a member sizes, then you go through detailed connection design to make sure your connection is ductile. This kind of design philosophy is what we call the equivalent static force procedure. It has many merits, a lot of good advantage. One, it's easy to follow. Almost almost all trained engineering can follow this kind of cookbook procedure that you can design the building from A to B to Z. It's like cooking. I don't do much cooking, and Professor Sturgiadinovi knows, and Svetlana knows. My wife cooked for my whole life, so I don't know how to cook. But I assume if you have to cook cooking pasta, you probably will boil a pot of water, you put X amount of water and put Y amount of pasta, you cook for certain time minutes, and you take it out. Building code is trying to do cookbook procedure, right, to design for earthquake. These are the A, B, C, D, E, F, G steps to follow. So it's easy to follow. And it also relies on elastic analysis. So it's really easy for engineers to do a simple model and they can analyze the force and deformation within the system. But it gives us a lot of questions. First of all, is the equivalent static force procedure really the right approach to do it? And if you look at this equation, this is what we do in Canada, RT and RO. In the United States, we simply have R factor. How do those factors be defined? To be honest, those numbers are actually, I couldn't say made up, but by experience. Engineer through experience in design, they know the moment resisting frame has certain reduction, ductility, and overstrength within, so it gives you a factor to design the form. Bear in mind, earthquake doesn't know how you design your building. It's going to count with the real earthquake force. So the RO value or the R value we use in the United States, is that really correct? Personally, I don't think it's true. Okay, so that's the first question that we have. Second question, does the elastic analysis still apply when the building goes highly nonlinear? Let us thinking again. And third one, which is I think very important, what is the performance of the entire building if you design through this cookbook procedure? The truth is that the performance, if you follow this cookbook procedure, is hopefully it will behave well. How well it will behave, we actually don't know. And most importantly, how do we use this kind of design approach for new systems? I mean, I'm sure Serbian has a lot of new ideas and technology, which is not one of this cookbook procedure. How do we start using this cookbook procedure in doing the design? So when I started thinking about that, when I came to Canada from California, I see a lot of novel devices, rocking systems, outrigger systems out there, but those cannot be designed with a cookbook procedure. So I started looking around all different methods out there. There are many methods out there, well-established method, that including EDP, Equivalent Energy Design Procedure, DDBD, Direct Displacement-Based Design. It's my understanding that you have seen this presentation from the New Zealander approach. PBPD is from Professor Subhash Goyal from University of Michigan. P-spectrum method is the one from University of Toronto, and ATA-charm method is the one by Professor Kasai from Tokyo Institute of Technology. By the way, EDP is the technology or the design method that I developed with my team here at UBC. Among all these different methods out here, they all understand that we should design a structure system. Design has to be simple. You don't want to do a complicated computer model and figure out afterwards. At the very beginning, you want to have a good feeling how the building will behave. So we started with a single degree of freedom nonlinear system. So all these methods use the sand approach. And all these methods also had a very clear understanding. In order for you to design the structure properly, you need to have a very clear yielding mechanism of the system. So you wanted the beam to column to yield, the base to yield, so you have a plastic mechanism, okay? And then some method different from the other. For example, the PBPD method, the performance-based plastic design method by Professor Subhash Goyal, P-spectrum method and ATOM method will require engineer to have some rough estimation of the structure period, which is not a problem because right now it's not difficult for you to estimate the structure period, rule of thumbs, if you wanted to. So it's actually quite easy to achieve. But quite honestly, this is an approximate value which you need to do iteration to check. So only the DDBD and EDP, the New Zealand method, and the one here we have developed UBC, we don't require engineers to initially guess the structure period. We don't need to. And then the DDBD, the direct displacement-based design, will require engineer to have some preliminary sizing of the member, which is not a problem if you are a skilled engineer. We have a lot of experience. You roughly know what beam and column sizes you have. So in the next iteration, become very fast. But if the building is unique and you have never seen it before, preliminary sizing may be a bit challenging because you needed to do some iteration. And the P-spectrum method and ATOM method will all require you to do some nonlinear analysis. And almost all the design, DDBD, PBPD, P-spectrum method, and the ATOM method will require iteration. Okay? And the last two is that EDP will consider the design multiple level shaking intensity. So yes, we should be designing our building for the big earthquake. The one comes every 2,475 years. But the medium range earthquake and the small earthquake also have a significant impact to our building. So EDP method and P-spectrum method are the only two methods actually have a design which consider multiple hazards at the same time. So the performance will achieve at all different hazards, multiple hazards, while the rest is designing for the worst of the hazard. Okay, so you could also achieve multiple performance objectives at different hazards. So with the interest of today, I will only present to you about the EEDP method, which we have published in Earthquake Spectra in 2018. And this is one of the first paper we published about the design. And the title of that is called Equivalent Energy Design Procedure for Earthquake Resilient Fused Structure System. If you can find it, that's great. If you couldn't find it, you can write email to Professor Brazat, and I'm sure she can share the paper with you. Wonderful. So today I'm going to present to you the logic behind it. EDP, once again, is called Equivalent Energy Design Procedure. It's actually based on my training with Professor Sturgeon Novik when I was in Berkeley. We're trying to do energy equivalency. The energy from the outside coming to the structure should be the energy dissipated by the structural member. So we follow an energy-based design procedure. We allow engineers or designers to select a plastic mechanism. So we started to develop many different mechanisms. This is one of the systems we designed. This is a spline system where you have two structure fuses, one at the basement, where during the earthquake, it will dissipate energy, and the other one is between the beam to column connection. Similarly, we can apply EDP to the conventional concrete core wall system, where the first line of defense is the yielding of the coupling beam, and the second yielding is the yielding of the plastic hinging at the base. We have also applied similar technology for EDP for control the rocking system, where the system can rock and come back and stay and recenter. The idea behind EDP is to allow engineers to design the system to achieve different performance at a different shaking intensity. At a service level earthquake, we expect that the structural performance will be no damage, okay, or very minimal damage, so you can immediately occupy the building. At the design-based earthquake, only the structural fuses will yield or damage. Where there's no damage to the main structure, so we can return to use very quickly. In the maximum credible earthquake, we want the structure to have no collapse. So both the primary system and the structural fuses will yield to demonstrate that we can reach collapse prevention performance. Most importantly, we want designer to be able to size the beam and columns and the braces or the devices very quickly without computer, so they can do it by hand, and then they can size the dimension, and they can satisfy both the drift and strength at the same time without iteration. Because it's an energy balance method, so whatever you do, you will satisfy the strength and stiffness, strength and deformation at the same time, so you actually don't need to do any iteration. So it's not a force-based or displacement method. And it can be applied to many different structure systems, including new structure systems like the outrigger system, rocking system, and most importantly, we no longer need to make up what's the assumed the reduction factor for ductility and overstrength. So you can apply to many new systems now. Okay, so EETP is a 7-step procedure, okay, and I'm going to go through each one of them slowly. Professor Brezev says, let's go slower today, and everything's recorded, so people can come back, review the video again. So step number 1, so the whole idea is following these 7 steps, and you will be able to size your structure system, where the beam, the column, the fuses, and without iteration. So let's start with step number 1. Step number 1 is to understand what level of shaking intensity we are designing for. So in this situation, it's not difficult for you to find out by the building code or by the owner's perspective what level you are designing for. In the United States, most people will be designing for the maximum credible earthquake, and there's another factor which is maybe 2/3 of that, which is called the design-based earthquake. In Canada, we only design for the maximum credible earthquake. But right now, we allow engineers to actually select 3 levels of shaking intensity, standard for service level earthquake, design-based earthquake, and maximum credible earthquake. So if you don't know what you're designing for, you can follow the code for your maximum credible earthquake, and you can talk to your owner as well. I'm designing for your building. I want to know what performance level you're looking for. Your owner may say, okay, I would like to make sure there's no inspection. Well, maybe they should not say that. There's no damage to my building up to magnitude 5 earthquake. So you have a very clear performance objective. You should try all kinds of earthquake up to magnitude 5, around magnitude 5, and there's no damage. And the owner will say, I would like to make sure my devices, dampers will be working up to magnitude 7, and I want to make sure there's no collapse up to magnitude 9 earthquake. Okay? So those intensity can be defined based on the objective you're looking for. So based on that, you can easily define the design spectrum. So I draw a very simple cartoon representing the service level earthquake, design-based earthquake, and the maximum credible earthquake. The y-axis here is the spectral acceleration. The horizontal axis is the period of structure. Just very standard, typically what we do with the code. And now I'm going to replace the SA and period plot to the new SA and SD plots, which is nothing fancy. We have done that in the capacity spectrum design procedure. Instead of presenting your hazard in spectral acceleration period, you can present it in spectral acceleration and spectral displacement. So now, when I do that, the vertical axis is spectral acceleration, horizontal axis is spectral displacement. In reality, these may be jacketed a little bit, but in general, they actually increases radially out, okay? So why do I do that? Because I wanted to start turning into some units engineers have good feeling about. So if the y-axis I multiply by the mass, then the the y-axis will representing the force the structure are seeing, and the horizontal axis, the SD, if I multiply by the C0 factor, C0 factor is well presented in the FEMA 440 document to translate the relationship between a single degree of freedom displacement to the roof of multiple degree of freedom system, and everything about that is in FEMA 440. So it's a coefficient, maybe 20%, 30% from your spectral displacement increases to estimate the roof displacement of a multiple degree of freedom system. So now the y-axis will be representing the force the structure will see. The horizontal axis will representing the deformation of the structure at the roof of the multiple degree of freedom system. So this is our service level earthquake. So in this situation, you as an engineer already decided up to what level of shaking intensity there's no damage. So this line is well defined. So now you want to start designing your building for that intensity. So you start looking into your building and figuring out what is the maximum displacement that you could actually put in the building so your non-structural components are not damaged. So in this situation, you pick the drift, the non-structural component will not be damaged. So in this situation, there's an intersection between your demand curve and your capacity curve. So we want the structure to remain elastic up to that point. So up to this instance, you can quickly calculate how much is the elastic base shear the structure will have. So you can actually get from the intersection of the curve. Typically, the area under the curve is the energy from the earthquake. Over here, you already know spectral acceleration. You also know delta is also equal to C0 SD service level. So in these two situations, you know SA, you know SD, so you can actually calculate the period of structure once your demand is defined and you select your period, the displacement you want. So now the period can be calculated instead of estimated, and we will show you the calculation later. So now, based on this information, you select your intensity, you select the drift you want. Now you can calculate the period of structure and the elastic base shear. As I mentioned, the earthquake doesn't know how you design your building. If it can come with the force, will continue to come to the next level. So at this situation, if the earthquake increases to the design-based earthquake, then the area under the green area is the energy area because of the force deformation. The area under this curve is the elastic energy came from the earthquake. Okay, and this energy is easy to quantify. This energy is equal to this distance plus this distance times this divided by 2. So it's the area under the curve. So at this instance, we know that so much energy comes to the structure, and our job is to make sure that the energy dissipation devices need to dissipate this much energy. So we use the idea of conservation of the energy, where the energy came from the earthquake, which you can quantify based on your demand, should equal to the energy dissipated by your structure system. You may ask me, you say, Professor Yang, you just at this stage, how do you quantify the energy dissipated by the building? So I call it energy elastic, came from the earthquake, and energy nonlinear dynamic. So let's take a look. Energy nonlinear dynamic, if you take a look of the time history analysis of your structure, you plotted the energy dissipated by the structure over time. So you can see this area, the green area under the earthquake, is the energy nonlinear dynamic. And if you simply equate these two, then you could actually do further design. But at this stage, to properly quantify the nonlinear dynamic energy, you need to already know the structure members and the devices you choose so that you can do a proper simulation. By the beginning of the discussion, I say, this procedure do not require to do preliminary selection. It does not require to do time history analysis. So how do we do that? So at that time, we're thinking, okay, it's very difficult to actually quantify the nonlinear dynamic energy. But let's say if I wanted to have these energy dissipation devices, and I have the backbone property from the manufacturer, it's not difficult for you to quantify the nonlinear monotonic energy. So if you know the backbone, you can quantify the nonlinear monotonic energy. So our job is actually quantifying the relationship between nonlinear dynamic energy and the nonlinear monotonic energy, and there are some ratio to it. In fact, we have done a lot of simulation, hundreds and thousands of simulation, and quantifying the energy ratio between the nonlinear cyclic energy and the nonlinear monotonic energy. In most situations, it's ductility dependent, and we can have a chart like this. So with that, this becomes a constant value that you can look up on the chart. So now, if you assume energy will be balanced, so work done, this energy will equal to this energy. So in this situation, you equate the two energy, equation 1 equal to equation 2. The only unknown you don't know, because Fy you know, delta Y you know, delta P you know. So the only thing you don't know is the yield force of Fp. So in this situation, by this simple equation, you select the displacement you're yielding for, you select your performance of your damper, you can actually quantify what will be the yield force of your structures. Once again, the earthquake does not know whether you have damper or no damper. If the earthquake continues to the maximum credible earthquake, the story is the same. You can easily quantify the energy came from the earthquake, the additional energy, and that energy must be dissipated by the energy of the primary system to yielding. Once again, you say energy primary system equals to the energy externally, and you equate that, and you can find out what's the maximum displacement and see whether this is a sufficient design for you or not. So very quickly, without doing any calculation, you know your demand, you can actually size your member and get the trilinear force deformation relationship of your system very quickly. Without any computer, you can just do it by hand because everything is things you already know. So now you have this trilinear force deformation relationship. That's step number 2, which is calculate the base shear, which is calculated the trilinear force deformation relationship. Step number 3 is how much of these earthquake forces, how much goes to the primary system, how much goes to the secondary system. Here shows you the example of the force in the primary and secondary system. So primary system is the forces to our damper, and the secondary is the forces to the moment resisting frame in the example I showed you earlier. So in this situation, there are 2 equations and 2 unknown. This force plus this force will equal to this force because they are in parallel. And this force plus this force equal to that. So you have 2 equations and 2 unknown. So you can actually solve how much is the yield force for primary system, how much is the yield force for your secondary system. So you can calculate the total forces to your primary and the secondary system. So that's step number 4. Step number 4, then you know how much goes to the link beam, how much goes to the moment frame, and you select your cross mechanism. Step number 5 is that you have distributed your base shear to the height of the structure. There are many methods to distribute the base shear from the base to the height of the building. Professor Sturgianinovi actually teach me this method when I was a student. This is the method presented by Professor Subhash Goyal, where we actually distributed load in a parabolic manner so that we're trying to yield all the fuses about the same time. So when I started doing this procedure, I adopted the procedure what Professor Goyal did. So we distributed the forces over the height of the building using the distribution forces he provided. So in other words, you know how much the base shear your primary fuses need to take, and you distribute it over height of the building. Afterwards, you do what we do, the kinematic method. The work done by the external load by the displacement equal to the work done internal by the energy dissipated by my fuses. So work done external equal to fuse times the displacement. The applied force times the displacement. The work done internal equal to the shear link times the deformation within the shear link. So work done external equal to work done internal, and you can solve for the forces in each of the link beam. Last step, once you know your link beams capacity you need, then the only thing you need to do is very similar to the conventional design. You have the non-yielding element where you do a capacity design procedure where you're going to over-design the non-yielding element to make sure even when all the devices yielded, the non-yielding element will not yield it. That's it. So very quickly, you can size a high-performance system like the example I present you here, the link column frame system that we designed using EDP. And with these trilinear force deformation responses, we size the link beam, we size the beam, we size the column very quickly. One thing I want to show it to you, at the beginning, we expected the calculation from EDP will be 0.88, but when we do the final elements, sorry, I said it wrong. When we design it with the EDP, when we choose the service level demand and the delta SA, SLE, and displacement, our predicted calculation was 0.9 second. And after we did the final element simulation, and you can see the period are very, very closest to what we are looking for. So we're very happy to see that. So once with that, you size the structure system, next thing we do is that we wanted to see if the structure really behaved the way we do. So we did a pushover analysis. So we push a structure with the load pattern we want, and we push it from left to right. In the initial design, we want the structure link beam to yield around a roof drift ratio about 0.5%. And about 2% roof drift ratio, we allow the beam to column connection to yield. So we did a pushover. You can see this simulation shows you the link beam go from green to red. And then eventually when the force deformation reached about 2%, all the beam to column connection started to yield. You will say, wow, this is really cool. But if you really think about it, of course, this is the only way this building will behave because we designed them with a plastic design. We force the system to yield at the displacement we want. So that's why the pushover curve and the trilinear curve match perfectly. And that's great. But the next thing we want to see, you did it by equivalent forces you get by energy. How will it behave during earthquake? So we put the same model through earthquake. So we run the simulation through earthquake. You can see under the design-based earthquake, the link beam started yielding. So you can see they turn from green to red, but the moment frame remain elastic and it's no damage to it because it's a capacity design. And then when the earthquake increases to the maximum credible earthquake, you can see as the earthquake started shaking, of course, it is highly animated, amplified. You can see the link being yielded and the beam to column connection also yielded. So that's what we see as what we expected. So we did lots and lots of time history analysis, and we're able to show by this simple equivalent energy design procedure, you can actually size the structure to perform in the way you wanted, where at the design-based earthquake, only the link being yielded, where the moment resisting frame remains elastic. When the intensity increases to the maximum credible earthquake, the link beam will yield and yield more. Okay, bigger deformation, and also the beam to column connection also yielded. We then ran lots of time history analysis. I think we ran 50 ground motion to it. And then you can see on average, the results will be, deformation will be varied through time history analysis, nonlinear time. But on average, you can see this is the median response of the time history analysis. And we demonstrated under this kind of a simple design procedure, even though the ground motion are highly uncertain, you can see the performance of the building are very well controlled by this plastic design mechanism. Once we did that, we continue doing with more and more research. And thanks to Professor Stojedinovic through introduction to Professor Subhash Goyal, Professor Goyal started working closely with me on many new innovative systems. So buckling restraint knee brace truss moment frame is another innovation that Professor Goyal and I and his former student are working together. So that including King Mongkut University Sutali and IIT Kanpur. And we initiate the research, and we are very lucky to get funding from both AISC and CISC to develop this high performance system. It's a very long name, Buckley Restraint Knee Brace Truss Moment Frame, a short term BRKBTNF. It's still very crazy, hard to sound it out, but Professor Subhash Goyal loved it, so I don't dare to change it. So it is the name it is now. So why do we do that? First of all, we were thinking truss is very good. We see that in airports, we see that in stadium, they spend a big distance, and architects love it. Architects love this total openness and total flexibility. They can do things, so they enjoyed it. If we can invent a system without column, they will love us more, but we haven't figured out how to do that yet. So, but truss is not a great system for energy dissipation. A lot of time, if the truss buckle locally, the behavior is not very ductile. So at that time, Professor Subhash Goyal and I were thinking, how do we do that? And we end up developing this BRKBTNF system, where we try to utilizing the truss to span the long distance we need. But in order to enhance its seismic performance, we started developing energy dissipation devices. And at that time, we don't want to over-invent the wheel, so we started using Buckley restraint braces at the corner of the frame where they can dissipate energy. And just around the beam to column connection, the truss and the column connection, we use the conventional yielding devices that Professor Tujadinovic has done a lot of this kind of research. So in order for us to first understand that at that time, we started developing high-end computer models in OpenSeas. And through that, we started developing computer models in OpenSeas that you can actually simulate very well the behavior, the kinematic and isotropic hardening of BRB. And it matches very, very well to the experimental result we see. So after we are done with that, we are very happy. So we started using that into the system. Once again, we use the EEDP design procedure, where we design the first link of yielding is the BRBs, and the second link of the yielding where the beam to column connection were actually yielded. And this is the design, and this is the pushover. And you can see the pushover resemble very well the design. And in fact, all the trusses, all the BRB yielded around the cluster, and the beam to truss connection and column to truss connection also yielded as a secondary fuse. You may ask me, why do they not all in the same location? Because at that time, we try to simulate variability in the structural strengths. So we do a random distribution of the strengths. And then so in the event of pushover, some BRB have a little bit higher strength than the other. It's normally distributed. So they yielded, but you can see the system, once one yielded, it passed the forces to the other, and they all yielded around the same cluster. Similarly, the truss to column connection all yielded as well. We then ran a lot of time history analysis to it. We select ground motion for the service level earthquake, design-based earthquake, and maximum credible earthquake. This shows a movie of the OpenSeas Navigator program that we developed to simulate the behavior of the BRKB truss moment frame. You can see as the structure started shaking, the BRB go from green to red, they started yielding, and then go from red to black, each fracture, and the force is able to pass to another system. So we ran through lots of simulation, and on the service level earthquake, this is the yield line. So you can see in the service level earthquake, we can see all of the earthquake, all the BRBs and the moment hinges do not yield at the service level earthquake. On the design-based earthquake, from all this earthquake, the moment hinge do not yield it, and the BRB yielded. So we can actually go back and replace them very quickly and achieve the performance we want. Under the maximum credible earthquake, you can see all our BRB already yielded, and we expected more of the moment hinge will yielded, but most of it yielded also. So we achieved the collapse prevention performance we want. We then look into the target drift displacement, and you can see from all these range of earthquake, we can see average. I think this is our mean or median. I have to check it. But the target is dead on in the elastic design, and the design-based earthquake were very close, and also the maximum credible earthquake. So this example shows to us this EDP design procedure is very simple for you to size the truss, the columns, and the BRBs, and then you just run it, and you will actually achieve the performance what you're looking for. Afterwards, we started doing a lot of experimental testing. In fact, we developed the hybrid simulation technology. Once again, I credit to my advisor, Professor Sujatinovic, who teach me and train me and push me to develop hybrid simulation technology. And we took the technology to Canada now. And basically, the BRBs are tested in my laboratory while everything else is modeled in the computer. So you can see in the event of the surface level earthquake, the BRB remains elastic, the moment hinge remains elastic, and during the design-based earthquake, the BRB yielded during our testing, and the moment hinge remains elastic. Under the maximum credible earthquake, the BRB yielded a lot more. It's a new BRB, of course, and then the moment hinge also yielded. One thing that for some of you are doing hybrid simulation tests, this is also the first hybrid simulation test that we have developed to do what we call the switch control algorithm, where the hybrid simulation algorithm will do displacement control, and when it sees the force is very high, the stiffness is very high, it will switch to a force control. So it's a switching between force and displacement control algorithm. So after we demonstrate the system works in the simulation and experimental testing, we started working with the companies in town, where GTS is one of the old established steel manufacturing company in Vancouver, where we started developing this to be a lightweight, fast construction, and earthquake resilient infrastructures. So in here, the floor system, maybe I missed that. But anyway, so it becomes a high performance system that you can use. And you can actually be placing this modular structure system in the layout, and you can start creating very exotic buildings like the one we see in Las Vegas. Yeah. Another high performance system that I have presented for this talk today is about tall buildings. Vancouver has many tall buildings. In fact, when I started looking around, Vancouver actually has the fourth largest number of tall buildings in whole entire North America. The first one's New York, Toronto, Chicago, and then Vancouver. So we have lots of crazy exotic buildings in Vancouver. So we want to make sure all these high-rise building, tall building are also high performance. So we initiated a research 8 years ago. You can see 2014. We started looking into what are the typical structural system we use in Vancouver. And we realizing it's very similar to California. We're mostly using concrete core wall for high-rise building. So these are some typical drawings that we obtained from the city of Vancouver and the structural drawing. This kind of structure system came from New Zealand, where the idea behind it is that we will have the link beam to dissipate energy during the earthquake. So it will crush the link beam. And in the big earthquake event, we're going to crush the base to form plastic hinging. To be honest, when the high-rise building, when the link beam are all yielded and the base are forming plastic hinging, there's no way we can replace or repair this high-rise building, and it will all lead to demolition afterwards. So we scratch our head and say, how do we start developing high-performance tall buildings? So we started working with our engineers in town. RJC is the biggest structural engineering firm in Canada. So we teamed up with them and figuring out what will be workable and deployable in the setting like Vancouver. So after a few, many actually, now not just a few, many iterations with the engineers, we developed, and the engineer give us very clear feedback. Professor Young, we like all these innovative things, system you do, but we have to make sure it's buildable and can be used in Vancouver. And one of the message they tell me, the owners prefer to have concrete core wall, but we already say the concrete core wall are designed to be heavily damaged, and how do we deal with that? So after we scratch our head, we develop a few innovation towards that. The first, we know the link beam is designed to yield, so we develop a new coupling beam, which is a cell center friction-based coupling beam. It will dissipate, it will move during earthquake, dissipate energy, and bring building back to center. The high performance link beam. And we have outrigger system, and we also have the rocking devices at the base, so allow the base of the wall to actually uplift and come down without forming plastic hinges. We once again apply the EEDP design procedure to design how much is the fuses, how the concrete core wall, and develop the outrigger system. We have developed tons of simulation in different simulation to show the behavior of the structure system. And we also developed truly innovative steel link, self-center friction-based link beam, which allow the devices to actually move during earthquake and bring it back to center in all directions. Okay. So it's like a cone, male and female cone, you compress it, and when you start pulling it out, it comes back in all directions. We started with that design, and we did a lot of simulation and optimizing the curvature to come up with the shape we wanted. And this shows you a very nice simple view, shows that as the cone being pulled out, because the PT, it brings it back. So in all directions, it pulls it back. We then develop advanced simulation model to show without the devices, how will the concrete core wall rocks during earthquake. And we develop a new devices at the base of the core wall to actually dissipate the energy to prevent pounding to that. Once again, we use the hybrid simulation technology to test those damper while everything else is modeled in the computer. And we did all the simulation and we're still not satisfied with that. So we decided to build a large scale shaking table test to demonstrate the concept. So very different than many other research. We decided to build as big as we want of a scale model to do. So our vision was a 30-story high-rise building, but we had no finance to build a 30-story building and crash it. And we can scale down the model significantly, but nobody will believe it. So through compromise, we developed a 1/6 model of a 30-story building. So it's still quite big. It's a 5-story building. We actually built it, and we developed the core. You can see our connection to our link beams, and we cast the concrete. And something really amazing is that I don't have the facility to test in Vancouver. And I happen to be the executive director for the largest earthquake centers in the world now. And they have big facility in China. So I built my concrete core wall in segments and shipped them to China and arrive the border and bring to the lab. When the device reached Shanghai border, the customer will blown away. What is all this about? We say, we're here to do testing, and this testing will be crushed and there's no value, and we actually go into the country without paying heavy duty. So anyway, in the big laboratory in Shanghai, where Professor Stojadinovic has been there for many times, we have big shaking table facilities. We bring our specimen from Canada and we assemble that on the structure, and we're putting our link beam and our rocking devices there. So it's a quite impressive study. In fact, this is the tallest concrete core wall ever tested, because most of the taller specimen they do are plenary wall, not a core wall. And actually the whole design was placed in the multi-shaking table facility in Tongji University. And the intent is that we design the high performance system to actually in the X direction and Y direction independently. And so we're going to shake the structure in the X direction and show the system works perfectly with no damage. And in the Y direction, it will be the same. And we want to do a bi-directional shaking to make sure you design them independently. How will they behave as a coupled system? And afterwards, we're going to take out our outrigger system and then allow just the base to simply uplift it with a simple energy dissipation. We expected performance would be not that good, but it will still be better than locking that. And we expected no damage to structure or very light damage. And afterwards, we're going to lock the wall down and then shake it and cause the structure to have significant damage, no different than the conventional concrete core wall we have seen. So we'll see very heavy damage. The testing, everything was getting ready to go, and COVID hit. So my team have the specimen in the lab, and it's still in the lab. We actually just about the testing. So as soon as the situation gets better, we'll go back and complete the test. So with that, let me give you some quick summary and conclusion. I'm happy to answer any question if you should have any. So first of all, I want to remind us, earthquakes is one of the most devastating natural disaster faced by mankind. Today, I show you some of the advanced technology we have developed for simulation experimental testing, and we have already pushing very hard in developing novel, resilient, high-performance system. They could actually be lower cost to build because you don't need to do so many detailing anymore. All the energy dissipation are by the device. They are higher performance both during the earthquake and after an earthquake. And with that, I'm pretty sure together we can start developing high performance systems that are more economical, more efficient, and robust towards future earthquakes. With that, I would like to thank you for your attention. And if you have any question, please feel free to write an email to me, talk to Professor Stojadinovic or Professor Svetlana Brezat. Both of them are great colleagues of mine, and I answered their email immediately. With that, this is my last slide, and I look forward to welcome you all to beautiful British Columbia, and I look forward to a chance to visiting Belgrade one day very soon. Thank you.
Thank you very much, Professor Young. It was an excellent and exciting lecture, taking us into the future, I would say, which is, it is present in some parts of the world, but for us, it is just the beginning of the future. So I would like to invite, it was really excellently presented, and you took time, which I really appreciate. It's great. So we have still quite a few people, 57 participants. And I would like to invite questions from the audience. Any questions are welcome. Do you have a few more minutes, maybe 10 more minutes or 15? You have, okay, thank you very much. So maybe do you want to ask question, Boža?
Yes. Let me thank you, Tony, for this great presentation, a fantastic overview. You mentioned me also many times. This is also to make sure that the doctoral students who are maybe in the audience don't think that they have to work so much to get their degrees, but that's why you're a professor. But there is one thing that you did not mention, and it's very, very important. It's also the work that you did. It is the development of the PACT tool, the PACT tool for FEMA P58. And it is something that we have mentioned several times in the seminars that SUZI did. It is the tool to estimate damage after an earthquake, including structural and non-structural elements. And it's a fantastic tool. It is now the standard. It is the way to go. And then you mentioned that in Taiwan, they value comfort and safety almost the same. Tell us how you could use the PACT tool in your energy system to show the benefit, the additional cost that you do for the primary and the secondary system, and the benefit it gets you.
Thank you. And it's always a very good in the industry. They always assume these energy dissipation devices or high performance systems are more expensive. They may not be true anymore because there are many reasons they are not. First of all, if you think about the way you do, for example, this high-rise building we did. If you don't do these rocking devices, you spend a lot of money with this foundation where they are very heavy. Now you allow it to lift a little bit, so it actually reduces demand for the foundation. They become cheaper. You reduce everything above, it becomes cheaper. So now we can demonstrate the initial costs are cheaper. at least neutral at the moment to see they are not always more expensive. But sometimes you have to demonstrate, if I'm owning the building for the next 50 years, is that really pays for itself? And so the tools of Professor Stojanovic mentioned is a tool allow us, and he's too nice. He actually guided me in doing it, even though my name is in the front. But we actually developed a procedure for us to actually quantify financial losses. So now you have this fancy building versus a traditional building, and you can use the tool, the PAC tool, to study innovative system versus the conventional system. And it gives you a distribution of structural damage and performance. And with that, you can actually figure it out in the life cycle use of the building. Maybe the conventional system started here, but the new system started here. But over time, it actually crossed. So you can see if you're owning the building, you can actually see it pays for itself to do that. In fact, we apply that in many of the buildings that we do here in Canada. Bosha, thank you for your guidance. I put in the base isolation things with Svalana into the building code, but I also designed the first museum for base isolation in Canada. Now it's in use. So now we demonstrated it actually can actually pay for itself now. Yeah.
Thank you, Tony. Thank you very much.
Thank you. Thank you.
Thank you. There is one comment more request from the audience, and there is one more new message. There one comment and request from Lazar Mihailovic is thanking you for, you can see in the chat, thank you for the great lecture and explaining this procedure. And it says that it will take time to rewatch the review, which is great. This lecture will be on YouTube, like all previous lectures that SUZI had. And but he is asking if about the literature for related to EDP and even buckling restrained knee brace truss MF. So if you don't mind, because we'll have a web page for this, we'll continue to have a web page for this your lecture, where we will post slides if you permit, and maybe we can include links to some of the we cannot share since these are journal papers and all that. But I will work with you to get some to put it together, if so that everybody who is interested can have and I can create it and then you can add. So we will have on that same page that you currently see announcement for Professor Young's lecture, there will be a link to YouTube presentation, to slides posted, and then some links to the to the papers, if I believe that is okay for the journals. And if you cannot access them, you can contact SUZI. We'll share with you privately on that. So there is one more, I believe, question on. So some people are asking on chat. So I will read the question by Veljko Simic. It says, I think equivalent energy design procedure is much more applicable for checking old building resistance level to earthquakes instead of using it for new building design. Am I right?
If that's the question, I would say it can be applied for both. Yeah, you can apply for a new system, and you can, and this system is very easy applicable to retrofit if it needed to be.
Thank you, Tony. I have a question about this design procedure. As you mentioned, for example, in countries like Canada, only since 2015, there are provisions that permit officially the use of systems like this one. How do you see the place of this system? I mean, as you know, Canadian code, for example, and so on, the other codes have some requirements, provisions. Do you see this place? Of course, you mentioned both new and existing buildings, but then also, do you see it as a preliminary procedure that would be a companion to some more detailed analysis? Can you maybe explain how do you see that as a part of the design procedure?
Right now, most building code started going towards less prescriptive now. It's more performance, like goal oriented. These are the performance you need to achieve for. Of course, it's possible EDP could be one of the alternative procedure to do, but I would expect that the building code will be start going to be less prescriptive because EDP is still another procedure. It's very quick for engineer to size the beam and columns and fuses to achieve displacement and force at the same time. But still prescriptive because you do step by step. In the future, I would expect that the building code will be not telling you, well, maybe I don't know, I shouldn't say that. Now we're recorded. I'm just saying that. I expected the building code will be shifting towards, okay, in this level earthquake shaking intensity, you need to achieve this performance, and these are the procedure you need to demonstrate it. And then how you design it is on you. I suspect that's the trends in the future now. Yeah.
Thank you. Yes, and I believe that even for design, I had the opportunity or maybe good luck to be a part of a team that designed some of the first application of dampers in Canada, viscous dampers, not this type, but in any case, it is an iterative process when we design it. So it is very helpful to have, you have to start from something and you have to do some equivalent systems in order to estimate what are the capacities of the dampers and other parameters. So anyways, the procedures like this are invaluable for those who are designing, whether they're experienced designers or not, they will be necessary. Whether it's going to be officially a part of the code or not, that is another question. So I would like you to also, if you don't mind, any other questions from the audience? I have one question about the practical application, but any questions from the audience that is more critical, of course, I shouldn't, please go ahead, feel free. Professor Young is always very friendly and open to questions, and any questions from the audience. If not, I would just like to ask about these devices, various devices that you mentioned. Are they proprietary or not? I understand not, but can anybody design them without, having a permission?
I don't know. I show you so many different devices. The BRB are originally proprietary, but I think now is almost everyone can use it. I mean, there are so many new innovations out there, and if anyone from the Serbian side are interested about some of the new dampers we built here, just work with us. We'll be delighted to working with you in different capacity in design, testing. Anyway, yeah, happy to do that. Yeah.
Thank you very much. I think there is lots of interest since, as I said, this area is relatively new and up and coming here, and so that would be great. So if there are no other questions from the audience, I just can promise that we will share this after processing the video and the recording to share the video, share the slides if you agree, and links to other resources to further reading and learning for our colleagues from Serbia and the region. And I would like to thank you for an excellent lecture, and as always, and it was really a pleasure having you virtually. I really look forward to your physical visit to Belgrade, Serbia, and of course everybody wants to visit Vancouver as well, but we would like to welcome you in Belgrade. Thank you very much, and thanks to all the participants for attending this lecture. Thank you and good night.
I look forward to seeing you in person one day very soon. Thank you. Bye-bye. Good night. Good night. Bye-bye. Bye-bye, Svetlana. Bye-bye, Boja.
Bye-bye.
Okay.